reconstruct shapes from unseen classes. And this is going to be jointly presented by Jiutong Zhang and Xiuming Zhang. And Jiutong will go first.
Thanks. Good afternoon, everyone. We would like to introduce our work on learning to reconstruct shapes from unseen classes. This is a joint work with Xiuming, Chengkai, Josh, Bill, and Jiajun. So given a single image of an object, human can easily imagine the 3D shape of it, even if a major part of the object is not visible. One of the hypotheses behind this ability is that we learn to hallucinate the 3D shape of an object based on our past experiences. Instead of memorizing them, we learn to predict the 3D shape of an object based on current perceptual information. And such ability generalizes well even to objects that we may have never seen before. Recently, computer vision researchers aim to mimic such ability by training a neural network with large CAD model datasets and rendered images. More specifically, most past approaches fall into the general category of minimizing some loss functions between the predicted shape and the ground truth one. Since the mapping f theta is usually hard to learn, previous works have proposed different loss functions, learned priors, or extra supervisions to facilitate this process. For example, two very recent approaches, called DRC and AtlasNet, use different representations, loss functions, and training paradigms to approach this problem. On training classes, their model performs quite well. However, if the input image is not from their training classes, for example, a table, both algorithms fail to give reasonable explanations. And they give outputs that are very similar to their training classes. More importantly, both algorithms' predictions fail to explain the input image, which is not a desirable behavior. In some sense, such behavior can be viewed as a severe overfitting over the training classes, so a proper solution is to add regularizations to the function f theta. In our work, we show that introducing proper inductive biases to the mapping f theta is a very effective approach. Specifically, our choice of inductive bias is inspired by the forward image formation model. To take an image of the 3D model, one needs to first specify some camera and lighting setup. Given this setup, light rays emits from the light source, then hit the surface of the object and reach the camera. However, only the information of the visible surfaces reach the camera. Taking an image is then projecting these visible surfaces from 3D space to 2D image space. Given this two-stage process, we can design an inverse model accordingly. First, given a single image, we can first infer the 3D information of the visible surfaces by estimating its corresponding depth map. Then, we aim to complete these partial visible surfaces back to the original shape. This gives rise to one of our previous works, where we use two separate neural networks to first estimate depth information from a single image, then use another network to predict the final shape using the estimated depth. However, we observe that the second neural network, under such design, is always over-parameterized, as it has to implicitly learn a deterministic projection process, which is essentially parametric-free. As the depth image can always be projected into 3D space, we can explicitly perform this operation in a fully differentiable fashion and let the second network only perform surface completion in 3D space without having to learn this process explicitly. But we empirically find this approach problematic as the partial surface is very sparse in input space. It's very hard for the network to capture local surface features and to perform the job efficiently. To overcome this, we introduce a surrogate representation of 3D surfaces called spherical maps. The spherical maps are defined as projecting 3D surfaces onto a unit sphere. Specifically, given a sparse surface in 3D, we first initialize a UV discretized unit sphere around the origin. Then, for each UV coordinate, we shoot a ray towards the origin, record the distance it traveled till hitting the surface of the object. Through such operation, we encode the 3D surfaces on a 2D manifold where the surface information is no longer sparse. Using this representation, our proposed model, called generalizable reconstruction, short for GENRA, first predict the depth information from a single image, and then we use a deterministic projection process which converts the depth image into spherical maps. Then, we use another neural network to complete the object surfaces in spherical domain. However, as special spherical projections does not represent 3D surfaces in a lossless fashion, where regions of self-occlusion is always ignored. Therefore, to give the final estimation, we project the predicted full spherical map back into 3D space and use a third neural network to refine the self-occluded regions. This is an overview of our proposed model genre and its design motivations. Now Xiuming will elaborate on our training paradigm and evaluation experiments.
We like to highlight a distinction in supervision type crucial to generalizability, object-centered supervision versus viewer-centered supervision. With object-centered supervision, the model always learns to predict the 3D shape in its canonical pose, regardless of the input view. Take this table as an example. If our input view changes, the 3D shape supervision remains the same. In this case, the model is actually solving an easier problem where some voxels are consistently occupied or empty across different tables. As canonical pose is class-dependent, object-centered supervision is not suitable for generalization. This has also been observed by Xin et al. In this year's CVPR. In contrast, viewer-centered supervision requires the model to predict not only the 3D shape, but also its 3D pose. So if our input view changes, your supervision rotates accordingly. Although this makes reconstruction more challenging, we believe this is the right way to go for generalization, since canonical pose is not really defined for an unseen class. Before talking about generalization, let's warm up with objects from training classes. Here are the 3 single images and their corresponding 3D shapes. We compare with differentiable reconsistency, or DRC for short. It was trained using viewer-centered supervision, same as ours. We also compare with the state-of-the-art AtlasNet, which was trained using object-centered supervision, as it tends to predict unstable results when viewer-centered. AtlasNet here is able to reconstruct a stereotypical shape of the correct class, but lacks specific features present in the input view, such as the curvy chair base. Here are the reconstructions by genre. The left column shows genre reconstructions are view-aligned with the input images, which brings great advantage in generalizing to unseen shape classes, as we will show soon. Note how genre is able to preserve the specific shapes features, such as the car's top light, the airplane's engines, and the curvy chair base, by exploiting the only views available. We've also quantitatively evaluated how the 3 models compare using transfer distance, which is the sum of closest point distances between the reconstruction and ground truth. As these objects are from the training classes, the object-centered AtlasNet exploits canonical poses, outperforming genre by 8%. But what about the novel classes that are never seen during training? Take sofas as an example. We are pushing AtlasNet to a region where it's not designed to work, and indeed it doesn't. The L-shaped sofa got reconstructed into a chair. But our model is designed to generalize to unseen classes, and we see it does generalize to sofa, despite having never seen one. Notice how the sofa back, despite non-visible, gets reconstructed to be a smooth plane. How did genre do that? Completing a non-visible surface in 3D is actually easy in the spherical domain. The non-visible sofa back shows up as blank or missing values in the partial spherical map. And our impeding network then guesses the missing values in a smooth manner shown on the right. This operation basically completes the non-visible 3D surfaces. Here is generalization to bookcases, desks, and loudspeakers. Genre reconstructs shapes that correctly represent the novel task categories. Quantitatively, reconstructions by genre are over 26% better for these 3 novel classes. Here are more comparisons. Note how genre preserves the detailed structures visible in the input views. We further test genre on non-rigid shapes. As a reminder, it had seen only cars, chairs, and airplanes during training, which are all rigid shapes. For this experiment, we used depth as input. Genre completes non-visible parts of the human and the horse, utilizing generic shape priors learned from rigid shapes. Since our model preserves what is present in the input view, it's natural to ask how the input viewpoint affects generalization. So on this view grid, if we traverse horizontally, we are viewing the object from varying azimuth angles. Similarly, the vertical axis represents change in the elevation angle. Now we can compute the average reconstruction error for the novel class of tables as a function of azimuth and elevation, with darker colors representing larger errors. The view enlarged here is an accidental view from which we have no clue what the table legs look like. As the heat map shows, accidental views lead to large reconstruction errors. In contrast, the green view below reveals its legs. We therefore call this view generic. Reconstruction from generic views have lower errors, consistent with our intuition. We hope this heat map could highlight the importance of input views in the problem of single-image 3D reconstruction. So in conclusion, what's cool and new here is genre generalizes to unseen classes. That means you can train your models on cars, chairs, and airplanes, and then reconstruct a 3D bed or 3D table from its image. We did this by imposing stronger regularization, using a more compact surface representation, and exploiting conditional independence. Thank you all for your attention, and please visit our poster for more.
We have time for a couple of questions. OK, let me start with one. Thank you for the very impressive work. And one question I had was, have you actually tried explicitly characterizing how well your model generalizes to new classes by, for instance, training your own model on the unseen classes and then comparing the performance? And which of the 3 stages of your pipeline would benefit the most, do you think, from being able to see the new classes?
Thanks for the question. So in the paper, we have done tons of ablation studies to evaluate different stages of contributions to the final generalization power. So welcome to visit our poster, so we can give a more detailed explanation on the experiments. Thanks.
And I think I would also like to add to that question. So essentially, I think the most important component here that allows you to generalize is really by reconstructing the object in its original view, so that you could actually project what is visible in the original image back into the 3D place. So this is one of the ways to ensure whatever you see is definitely preserved in the reconstruction.